Hello. Good afternoon. Welcome to the afternoon session. It's my pleasure to introduce the next speaker, Glynn Winskel. He is a professor of computer science and fellow of Emmanuel College at Cambridge since 2000. He read mathematics at Cambridge and mathematical logic at Oxford, and then he went to Edinburgh for his PhD, where he graduated in 1980. He is in the executive advisory and editorial boards of several journals and conferences. He's done a lot of work in different areas of theoretical computer science, in particular formal semantics, concurrency theory, and broadly speaking in the foundations of computer science. He is also the main founder of the Briggs Research Center, where, for instance, Frank did his PhD, and Pavel as well, so they owe you for that. And his production in terms of research is impressive. He's the main author of one of the main books in formal programming language semantics, and he's written more than 100 papers, a lot of them as a single author, so he's done a great work. And he has numerous awards as well, including, for instance, the Test of Time Award of Leeds. And recently, he was awarded, well, recently, like 4 years ago, he was one of the very few UK researchers who was awarded an ERC Advanced Research Grant. He's, as you can see, an excellent researcher. He's a very good teacher, I know that, and he's also a very good friend. So let me introduce you, Glynn Winskel.
Yeah, thank you very much, Julian, and it's a pleasure and honor to be here. Quite a privilege, in fact, so thank you. Well, I'm going to be talking about distributed games, where you can think of, they're going to be two-party games, where you can really think of it being between player, or really a team of players, and opponent, or really a team of opponents, interacting in playing a game in some kind of distributed way. And the reason for the interest in such games in computer science is that because we're often concerned with systems or processes in which we have control over certain moves, certain events that we can do, but other events are just left open to the environment. So those events that we have control over, we often think of those as player events, and those on which which are really under the influence of the environment, we think of as opponent events. And I'll be looking at how to model such distributed games, and also how to put probability on them. And the original motivation for this was really the realization that traditional domain theory and denotational semantics had really perhaps had its day. It was very good for functional programming, it was very good for various things, but it had its limitations. It had perhaps abstracted away from operational concerns too early and so on. So there's a need for a new foundations for semantics, and one of the candidates that I'd like to propose is distributed strategies between distributed games, on distributed games. So the aims of this enterprise are really severalfold. One is to try to repair the divide that's developed between denotational semantics and operational semantics. And I think that's arisen because denotational semantics just abstracted too far from operational concerns too early. Then there's this issue that we have in our subject, the big divide that we have in our subject between algorithmic concerns and semantic concerns. And I hope at least that the common vocabulary of games will at least help bridge that divide. And then there are, within traditional denotational semantics, several anomalies that have occurred. One is just the observation that if you're looking at models for concurrency, things like Petri nets or event structures or whatever, then they're just too big, in some sense, to fit inside a domain as points of information. So they were struggling to really fit inside domain theory. We need some kind of expansion of domain theory to accommodate them. Then there are some other anomalies like non-deterministic data flow. You can give denotational models, but only at the expense of going way outside traditional domain theory and denotational semantics. And then in traditional domain theory, there's this problem of, if you have probability, of how to combine it with non-determinism, and how to combine probability with higher order processes as well. In fact, no one to date has a category for traditional domain theory and denotational semantics in which you can simultaneously do higher types and also do probability. So, and we'll, in fact, we'll be able to solve all of those anomalies in this talk. So, distributed games, what do I mean by distributed? Well, I've said what I mean informally, that there are these moves going on separated in space and so on, but how am I going to model that mathematically? Well, I'm going to do it by basing the behavior of a play not on the traditional sequences of moves, often alternating in traditional games, where you have player, then they have opponent, then player, then opponent, and player, and so on, but rather on partial orders of moves, in which you don't necessarily, come back, please. Yeah, oh yeah, in which you base the behavior of plays on partial orders, and don't necessarily, and where it no longer makes sense, of course, to think of following opponent, of alternation between opponent and player. And in fact, though, unlike the talk this morning, which was talking about causal understandings of Petri nets and was regarding a Petri net as a collection of causal processes, we're going to look at those causal processes as all being glued together in some ways in structures called event structures, which are like the generalization of trees, but to concurrency. Essentially, an event structure, or morally, an event structure is like a tree, but where the branches have the form of partial orders. And we'll see the technical definition in a moment. Okay. I mentioned this anomaly of non-deterministic data flow, and I'll just come back to it briefly, because the language we'll get for strategies will include a decent language for non-deterministic data flow, and will be a diagrammatic language of a similar style to data flow. And this was something that was unexpected. Traditional data flow, in which you have deterministic, is concerned with, if you like, boxes which are illustrated here in this picture. I've lost. Oh, got it all right. There we are. Boxes here, which you think of as having processes in them, deterministic processes in them, and they're connected to each other by channels, and along these channels they communicate by sending values, maybe streams of zeros and ones, or streams of A's and B's, and so on. And then they can be connected in any which way, quite complicated way, in this kind of way, so you can have loops and so on. So here, for example, we have a process G which is taking in a stream of data on the Z port here and outputting on the Y and the X port here, a stream of data. And this kind of thing was one of the early successes of traditional domain theory denotational semantics. Being concerned with solving least fixed points over or elements of a domain, one could easily write down a recursive definition of the behavior. And once you know what F and G are, you instantiate those because they're going to be computable, they have to be continuous processes on the streams of data, so you get continuous functions on domains, and moreover, you can then represent these unknowns here, these X, Y's, and Z's, as streams that will streams of values, and you can solve what those streams are by just taking these fixed points. So Kahn was early to spot this, and as I said, it was one of the early successes of domain theory. But in this picture, there's a surprise, because as soon as you start putting non-deterministic processes in for F and G, you can no longer do it with traditional domain theory and denotational semantics. There are solutions, you get denotational models, but only at the expense of moving outside traditional domain theory and working with, if you like, relations which have more intentional information. They don't just talk about relations between input and output, but they say how input is related to output. And what we'll get as a byproduct of what I'll be talking about will be a treatment of non-deterministic data flow and probabilistic data flow. Well, I'm going to base this talk on this fundamental model of event structures, which is as I said, like the concurrent analog of trees. Just like when you unfold a transition system, you get a tree. When you unfold a Petri net, if you take account of the branching behavior, which wasn't done in the Petri net talk this morning, if you take account of the branching behavior, you get an event structure. Okay, so it's like all of those causal stories glued together. And here is what it is. An event structure consists of a set of events, or strictly speaking, event occurrences, E, which are related by a relation of causal dependency. So when you see something like this, E prime below E, what it means is in order for E to occur, it needs the prior occurrence of E prime. E causally depends on E prime. Then there's, in order to account for non-determinism, you don't want all occurrences, all patterns of events to be consistent with each other. So we have a consistency predicate here, which picks out those finite subsets of events that can occur together. And if a finite subset is not in that consistency set of consistent sets, then it's inconsistent or in conflict. There are some reasonable axioms that you can associate with event structures. One is if you look at the events, the set of events on which an event depends, that should be a finite set, a kind of axiom of finite causes, and then some other ones that say, for example, that singletons are consistent, subsets of consistent sets are consistent, and that essentially this is saying that the downwards closure with respect to causal dependency of a consistent set is itself consistent. Now, because we're working with a partial order model here, we've got a direct interpretation of what it means for events to be causally independent or concurrent. Namely, if they're consistent, so they can occur together, and neither one causally depends on the other. So they sit side by side in a consistent fashion. When it comes to games, for technical reasons, the relation, this relation of immediate dependency, which is causal dependency but without, strict causal dependency but without any events in between, will play a special role. So I'll draw attention to that now. Now, as accompanying these intuitions that I've tried to very quickly give you an idea of, an event structure is associated with the notion of state. So you're looking at a process or system in terms of these event occurrences, and you imagine at a certain stage of looking at the events that have occurred at a certain stage of computation, they will naturally be consistent in the sense that if the set of events you've seen is X, then any finite subset should be consistent. And moreover, if you've been attentive and you've seen event E, then you should have seen all of the events on which it causally depends. So the set should also be downwards closed. So we take a configuration, our notion of state here, to be downwards closed, consistent subsets of events. And you can think of these as representing partial order histories. They inherit the ambient partial order of the event structure, and they give us like a partial order history, and moreover there's a notion of extension of one history to another one, just given by the notion of a subconfiguration, by inclusion. We'll often concentrate on just finite configurations. So here's an example. I mentioned streams of zeros and ones. This is like a tree-like data type. This is how you represent it as one of these event structures. You could either have 0 or 1 initially, and we're representing the inconsistency of those two things. They can't both occur together initially as the first place in the stream. So we represent that inconsistency or conflict by this wiggly line here. And then we have immediate causal dependency. Once you've seen 0 in the first position of the stream, you can see either 0 or 1 in the second position, and so on. And you can see here that if we take the configurations, they've got to be downwards closed and consistent, so they're going to correspond to branches, which are single branches, which might well be infinite branches going all the way up. There's also the empty configuration sitting there at the bottom. Because we're working with this partial order model, if we were to take, for example, the stream of streams of zeros and ones, and then put it in parallel with streams of A's and B's, we just do that by juxtaposition of the two event structures in this fashion. So if you think of a configuration here now, the downwards closed subsets would consist of a branch here and a branch here, paired together. Just to emphasize the greater generality of event structures, you can have situations where a single event depends on several events here. This event requires both this and this to occur previously before it can occur. If this event occurred, then it would stop this happening. So the only other event that it could occur, it happens to be concurrently with, would be this event here. And then consistency, although in the examples I'll often draw inconsistency as being a binary relation, just because it is in those particular examples, consistency is not necessarily determined in a binary way. We could have, for example, 3 events which were pairwise consistent, but not altogether consistent. Now, when you talk about structures, it's very sensible to think about what the relations or maps are between those structures. And we'll do that here. There are various structural maps of event structures that have now been around for about more than 30 years. And they first arose in trying to understand relations between compound processes described as event structures and, for example, parallel compositions, and how they were related somehow to behavior in the components. So for example, a parallel composition, you'd expect it to be subject to the constraints which you got by projecting into the component. Anyhow, here's what a structural map of event structures is. If you've got 2 event structures, E and E prime, then a map of event structures is a partial function. If you think about projection from a parallel composition, you won't necessarily always be able to make sense in that parallel composition in terms of an event in the component. It may be invisible in that component. So it's a partial function between the events, which is such that it sends states to states. In other words, it sends a configuration X by direct image to a configuration of the domain X by direct image to a configuration Fx in the codomain. But more than that, there's an extra little feature in these maps which is important, which is expressing the atomicity of events. It says if you have 2 events in a configuration and they go under F to something defined and equal, then those 2 events have got to be equal. So it's an injectivity, a local injectivity condition, because it's local to the configuration X. Notice, if F happened to be total, then that would mean that there would be a bijection between the configuration we start from and its direct image under F. F itself would restrict to a bijection between the X and the F of X. Now, turns out that these maps, as you'd hope, preserve concurrency, and that's really because they locally reflect causal dependency, in the sense that if you have 2 events in a configuration of the domain, and they're causally related in this way in the codomain, then they have to be causally related in the domain. That's in order to send downwards closed subsets to downwards closed subsets, which you need to do if you're going to send a configuration to a configuration by direct image. In general, it's not the case that these maps of event structures preserve causal dependency. You can have 2 events which are related, one dependent on the other, and they can go to independent or concurrent events. That's possible. But sometimes we want to specialize and look at so-called rigid maps which do have that property of preserving causal dependency. Now, I'll be using these maps later on in discussing strategies in games, so they're quite important. They're important also because they give us 2 operations we'll need in composing strategies. One is a kind of parallel composition due to pullback, and the other one is a hiding operation. So pullbacks arise, they're given categorically, and what I'll do is, they arise very naturally when you're considering 2 systems, say A and B, which have a common interface, and you want to consider the joint effect of setting them in parallel. So here we're thinking of 2 systems, one represented by an event structure A, one represented by an event structure B, and them having this common interface C, and the relation with the common interface is expressed by these two maps, F and G, saying how events A appear in the interface, and events B appear in the interface. And the pullback is going to be a kind of synchronized composition. The events of P are going to project to, an event of P is going to project to an event of A and to an event of B. So an event of P is like a synchronization event of the form A paired with B, where A is, of the form A paired with B, which is such that they go to a common interface event here. So the events of P are going to be built around pairs of the form AB, where F of A equals G of B. Okay? And configurations of P, they will correspond to subsets of these pairs, which are such that they will project to a configuration X of A and Y of B in such a way that that subset of pairs is actually the bijection given by the fact that f of X has got to equal G of Y. And we have, as I mentioned on the last slide, we have this bijection between F and F of X and Y and G of Y. They happen to be equal, so we get a bijection between X and Y, which is giving us a set of pairs, little a, little b. And so the configurations of P correspond to such sets of pairs, but not just that. They're going to be sets of pairs of sets of synchronizations, if you like, which inherit causal dependencies both from A and from B. And if we're not careful, these causal dependencies can work together to give us loops, causal loops, in these synchronization events. So we look at the loop-free sets of pairs given by this bijection here, and those are what the configurations of P, of the finite configurations of P correspond to. Okay? Now, there's quite a lot going on in this construction, but if you take away from this that pullback is a kind of synchronized composition, which is somehow respecting the interface, that might more or less do it for you. We also will need to have a hiding operation, and this will come about from a factorization property of maps. If we have a partial map, general maps of event structures are partial, if we have a partial map going from E to E prime, then we can look at the part of E at which F is defined. Let's call that V. And then we can just take the mathematical restriction of E to that defined part. So we just restrict the causal dependency and consistency of E to V. And we'll call that guy, this thing here, E projected to V. Now you can see that original map is now going to factor into two parts. One is the part that just caters with the undefinedness. It will just take the events of E to undefined and the events of E which are defined just to their copies inside this projected part. And then there'll be a total map then that goes from this defined part, which is just acting like F, okay, going to E prime. So it just continues like F, but it's now defined. And and we'll call that defined part, naturally enough, the defined part of F. And this will give us a useful construction which we'll be using in a moment. Okay, so now we're coming to how we're going to represent distributed games. We're going to represent the behavior of distributed games by event structures. But we have to, these are two-party games, but we have to distinguish which events correspond to player moves and which to opponent moves. So we'll give a polarity to the events. The player events will be plus events, they'll be positive, and the opponent events will be minus, will be tagged by minus. And we think of the player events, as I said before, as those events over which we have control, and the opponent events as those over which we have no control. Now, if we've got two games, we can put them in parallel. We know how to, we see lots of examples of this. Think about simultaneous chess. And we can do that here if we have two games represented by event structures A and B. We can just put them side by side, as I did with that streams example. And that gives us a simple composition of games. We also, there's another very important operation of games, these two-party games, which just interchanges the role of player and opponent. So we can take from the dual game just by reversing the role of plus and minus. And this will play a very important role in telling us how to build a category from strategies within it. Okay, so I've told you what games are, I've told you about the two principal operations we'll be using on games. What's a strategy in a game? Well, I won't tell you immediately what a strategy is, but I will say that it's going to be a special kind of non-deterministic play in a game. And how are we going to represent a non-deterministic play in a particular game A? Remember, A is an event structure. Well, because of non-determinism, we can't necessarily take the play of the game as some kind of substructure of the game itself. It can be more complicated than that, so it might sit outside A. But of course what we want is that this strategy, this non-deterministic play, or which you think of as the actual moves that can occur, what we do want to do is show what moves in the game they correspond to. So we need a map. And what we'll do is we'll just take a map of event structures to do a total map of event structures to do that for us. Total map that preserves polarity. So here's a little example. Oh, by the way, a strategy in a game will be a special kind of non-deterministic play. So A is representing the behavior of the game, so like the possible. So let me give an example, it might help. So here's a game, very simple game. We've got three concurrent events. Two of them are opponent moves, and one is a player move. And I want to have a strategy which says, if opponent makes a move, I answer it by making the player move. So here's a strategy for doing that. So I would say, okay, so this, the map will be the obvious one. These two guys go down here. These two guys go to these two guys here. And what this says is, okay, if I see the opponent move on the left, then I do this event. If I see the opponent move on the right, I do this event, and I make these in conflict, because otherwise I break local injectivity. So local injectivity here corresponds to the fact that if you can only do one move in the game, you can only do one move in the actual play. So is that okay, Moshe? Giving you an idea. So you can think of the configurations of the game A as being positions of the game, and you can think of the configurations of the event structure with polarity, S, as being states of play, where you are in the actual play. So this is actual play, and this is, if you like, potential play. And this strategy is informally saying answer is a strategy which is answering either move of opponent by a move of player. Okay, so now I've talked about a strategy in a game being a special non-deterministic play. I'll come to what special means shortly. And this is an important idea that's not as well known as it should be. You can also talk about a strategy from a game A to a game B. And this really, as far as I know, first arose in the work of Conway. And you take that to be a strategy in the compound game got by forming the dual game of A and putting it in parallel with B. So in other words, a strategy from A to B is a strategy in this game here, namely something like this, of a certain kind. All right. And Conway introduced it in his serial numbers in order to reduce, to show how to convert a winning strategy of one game to a winning strategy of another, so that he could get his serial numbers as strengths of games. By the way, I'm always going to be player. So when I talk about a strategy in a game, I'll be talking about a strategy for player. if I want to talk about a strategy for opponent, or a counter strategy, I'll mean a strategy in the dual game. Okay? Here's another very important example of a strategy. So this will be a non-deterministic play, and it will satisfy the extra conditions we'll put on those to make it a strategy. It's the copycat strategy. So you imagine, and this will function like a kind of identity with respect to a composition of strategies. So imagine we have a game represented by an event structure A. So it might be a big thing, but it may have these bits in it, A1 and A2 of the polarities shown. We want a strategy from the game A to the game, from the game A to the game A. So that's going to be a strategy in the game, the dual game of A, parallel with A. So here's the dual game of A. It's just the same as A, but we've changed the polarities around, and we've put it in parallel. And then what do we do to make the copycat strategy? What do we do to make the S part? We take that parallel composition and we add extra causal dependencies, so that the player move on one side or the other depend on the corresponding opponent move on the other. It takes some work to see that this gives you a partial order and gives you an event structure, but that is the case. Well, I should really say how consistency has got. You take events in this copycat strategy to be consistent if their downwards closure is consistent in both components. Now, it's not obvious, but there's a nice characterization of the configurations of the copycat strategy. And it's something I think it's important enough I've called it a special name, the Scott order, because it's reminiscent, and it sometimes plays, in special cases, plays the same role as the order of functions that Scott uses in domain theory. So you could ask, okay, given what I've said, what is a configuration of the copycat strategy? Well, it's going to break down into two parts, a configuration here, x1, and a configuration here, x2, and they're going to satisfy some property. Turns out that the property they satisfy is that they're in this relation here, which turns out to be a partial order. In fact, a complete partial order. It's given in this way. To go from x2 to x1 in the partial order, you drop opponent events and you add player events. And in fact, I could put something arbitrary in here and then show that if that was the case, this had to be the intersection here. Now, this happens to be a partial order, requires proof. Moreover, it's kind of intuitively related to the kind of order you see in traditional domain theory, because to get bigger, if you think of opponent events as being like a generalization of input, and player events as generalizations of output, then getting bigger in the Scott function order means giving either more output or giving less input, and that corresponds to giving less opponent moves or giving more player moves. So this requires a little bit of proof to show. Now, composing strategies. I talked about strategies, a strategy from A to B, something like this, and a strategy from B to C, something like this. There wouldn't be much point talking about them being from having this directionality if I didn't have a way of composing them. So the idea is to compose them roughly in the same way as you compose relations. If you've got a strategy from A to B, a strategy from B to C, you want to kind of synchronize them on the common part of play over B. And this is where we can use the magic of pullbacks. But not immediately, because you see, for pullbacks we need these to point to a common interface, and they don't. They point to different things. This is not the same as this. But if we pad out this strategy by putting it in parallel with the event structure C, and we pad this out by putting it in parallel with the event structure A, in this way, we do point to a common part, provided we ignore the polarities. Okay? And then we can take the pullback, and what this will do, this will have the effect of synchronizing these strategies over the common game B. So whenever sigma makes a player move on B, if that may synchronize with an opponent move that tau makes in B, and similarly the other way around. So this is a kind of synchronized composition, giving us, if you like, the composition of strategies, but not hiding. You see, that gives us a strategy which has got A and B and C, and it's got this B part in it as well. We really want, if we're composing a strategy from A to B and one from B to C, we really want a strategy going from A to C. So we want to hide the B. And how can we do that? Well, we can have a partial map going from here to A parallel C, just by taking everything in B to undefined. So now, going either way around the pullback, and then using this partial map, we have a partial map going from this pullback into A parallel C. If we take the defined part of that, when we reinstate the polarities, gives us the composition of the strategies sigma first and then do tau. It's quite a lot of technology here, but I think at least it illustrates some role of some kind of fairly useful role of some categorical constructions. Okay, so that's how we define composition. Now I better come clean. What are strategies? Well, we've got this copycat, and copycat should be identity with respect to composition. So, and it's not the case that if we took one of these arbitrary non-deterministic plays, that it would be such that when we composed it with copycat, we got the same thing back again to within isomorphism. We get the same thing back to within isomorphism if the original strategy satisfies two conditions called receptivity and innocence, which have some intuitive reading as well. What receptivity says is that here we have, it says, let me look at the diagram here, if you're at some state of play X, which goes to some position in the game sigma X, and in the game you can make some opponent moves from that to Y, that's what the minus is meaning here, so purely opponent moves to Y, then you can, in a unique way, extend X, necessarily by opponent moves, because maps preserve polarities, necessarily by opponent moves to X prime, which goes to Y. Okay? So it's doing the part that you often see in more informal presentations of strategies, where you say a strategy is such that for all things the opponent can do, I do this. So it's that. So that's what receptivity is doing for you. The other condition, necessary and sufficient to compose well with copycat, is innocence. It says if you have a causal dependency in the state of play, well, let me just say, it says that the only extra causal dependencies you can introduce in the state of play are ones that go from opponent events to player events. So the extra immediate causal dependencies are always of this form. So in other words, in order to compose well with copycat, you need to make this restriction that the additional causal dependencies are always ones of player moves await certain opponent moves. And these are necessary and sufficient to compose well with copycat. So that's what we take as our definition of strategy. And lo and behold, we get not quite a category of games here, because we're working with strategies which have a lot of structure. They have these S's, you see, which are event structures. So we don't expect to necessarily, when we do compositions, to get the associative law to holding on the nose, but we would expect it to hold to within isomorphism, and that's the case. We get a bicategory here. And moreover, because we have a bicategory and we have this structure on the S's as well, we have even maps between the maps, these so-called two cells. So we have this kind of situation. So if we have two strategies over a common game here, then we can relate them by a map in this way. And we get a bicategory. It has lots of nice properties, but I have to be a little quick, I guess. It has in particular duality, which says if you have a strategy going from A to B, then because of the obvious isomorphism between this and this, then that will correspond to a dual strategy going in the opposite direction between the duals. Okay? And this has some nice categorical features. All right. So come some kind of sanity checks. We looked at these are non-deterministic strategies. We'll need that non-determinism to be put probability on in a moment. But what happens when we look at deterministic strategies? Well, what are deterministic strategies in this context? Well, they should be strategies which are such that consistent behavior of opponent gives rise to consistent behavior of player. And we can say that technically in this way. And then we find in that situation that not all copycat strategies are deterministic. They are only deterministic if and only if the game that we work with is race-free. In other words, we don't have phenomena like this occurring, where an opponent move conflicts with a player move. So we don't get races between opponent and player to make moves. But in that case, we can cut this by category down to something that happens to be equivalent to a category. We can show those maps, sigma happen to be monos in this case. We get a category now. And in fact, it's something that was discovered in a slightly covered way. If you look at the receptive, ingenuous strategies of Paul-André Méliès and Sam Mimran, they're exactly these deterministic strategies that we get here. Another sanity check. If we do something stupid, like say, well, let's make the games really unfair. Let's assume that the games are only player moves. There's no chance for an opponent to get in there and do anything. If we do that, we find we get something else that corresponds very nicely to something that's known. We end up with something that's equivalent to so-called stable domain theory, invented by Gerard Berry and then popularized a lot by Girard and used a lot by Girard. And that's Gerard Berry's DI domains of stable functions. They're just equivalent to this sub-by-category in which we look at these stupid games where we don't give opponent a chance. Now, let's look at how we can, I'm afraid rather quickly, how we can make all of this probabilistic. And in doing this, we have to in fact solve some problems in traditional domain theory and decomputational semantics, namely how to combine higher order with probability and how to combine probability with non-determinism. Because you see, if we're working with probabilistic strategies, we won't necessarily, as player, be able to control the probability assigned by opponent. All we can do is attribute non-deterministic behavior to opponent. If you think of the matching pennies game, where we're in separate rooms and we're trying to just, I'm player, I'm trying to match whatever coin, if you have heads or tails, I try and match it. We have to be careful. We have to be, for example, such that I somehow would like to have that whatever I do probabilistically, if things are causally independent, then I would, if player and opponent moves are causally independent, then that's reflected by probabilistic independence. Okay, so we need to somehow add probability to event structures, but at the same time cater for non-determinism. Well, so first of all, let's look at the simpler case of adding probability to just plain event structures. This in itself is not so trivial, because no one's used to adding probability to trees. You just look at the branches out of something and then you put some probability distribution on it. That's that's well known. But here you see we've got concurrency as well. So what do we do? Well, there's an idea from domain theory that we can use here to give us at least a sensible definition of what a probabilistic event structure is. And it's an idea that comes about, I think, in probabilistic power domains. I think that's probably where it first appeared, in the work of Gordon Plotkin, or maybe Sahab Dajaroni. Okay, so how do we assign probability to event structures? This is not what we'll end up with. We'll end up with something equivalent to this, but this is kind of a reasonable place to start. Well, think about, now I'd like to draw, so I'm going to draw in the air. So think about the domain of configurations of an event structure. We've got the empty configuration at the bottom here, and then we've got these configurations above it, ordered by inclusion. Okay. Now, there's a notion of a Scott-open subset of such a domain, such a structure. What is it? In this particular case, it's got in the following way. You take a finite configuration and you look at all of the things above it. So it's like a cheese, like that. And then an open set, a Scott open set, is just an arbitrary union of these cheeses. Okay? Now, these are important because they correspond to those properties which are detectable in finite time, these open sets. And so what we'll do is we'll take a probabilistic event structure to be we'll take it to be an event structure together with a so-called continuous valuation on these open sets. And what that valuation will do, it will assign to each open set the probability of ending up in that open set. Now once you take that idea, there are some sensible things you expect. The probability of ending up in the open set corresponding to the entire space, that should be 1. The probability of ending up nowhere should be 0. If you have a larger open set, then the probability should be larger too. And then, of course, you've got this business of when you take unions, you've got this exclusion problem. That you can, if you look at the probability of U union V, where these are open sets, that's going to be not just the sum of probability of ending up in U and the probability of ending up in V, but you also have to, you've counted the intersection twice, so you have to subtract it. So you have to say this. And then there's another thing, which is really an extra condition, which says that the probability of an open set given as a directed union is just given as the supremum of the probabilities of the components of the union. That's an extra thing that's put in. So it restricts the kinds of continuous valuations you look at, but it's important. Now, because this is a continuous valuation, of course, if you take one of these cheeses that I talked about, these basic open sets which are subtended by a finite configuration, the continuous valuation will assign a probability to these. So in other words, it will associate with any finite configuration a probability of ending up above that finite configuration. And so a continuous valuation gives us an assignment of real numbers in the unit interval to finite configurations. But of course, not all assignments make sense. And on the next slide, I'm going to tell you exactly what assignments make sense and correspond to continuous valuations. And these will have the advantage of being more closely married to the structure of configurations of event structures, whereas open sets, of course, are one step removed because they're higher order. They're sets of sets, if you like. Okay, so this is the workable, this is the real definition of what a probabilistic event structure is. Now I'm drawing the air again. Okay, so we want to say, well, first of all, the easy thing is if we look at the empty configuration and we look at the probability of ending up above or equal to that, that should be 1. So that's okay. What's this nonsense here? Okay. Well, imagine you take a finite configuration Y. So that gives you a cheese looking like this. And then imagine you take x1 and x2 sitting above Y. They give you cheeses above, like that. And they may overlap. You can see? Maybe not. But anyhow, they may overlap. The condition says, in a situation like that, if you look at the generalized interval being above Y, but not above x1 and x2, in other words, this bit minus that bit and that bit, that probability should be non-negative. Of course it should. Okay? And that condition is necessary and sufficient. That kind of condition, when generalized to allowing not just x1 and x2, but x1 up to xn above y, that condition is what we're we're saying for these generalized intervals that their probability has got to be non-negative. That's what is going on here. So, so in other words, if you look for a generalized interval y below x1 up to xn, what's the probability of being above y and not above x1 up to xn? Well, because of this exclusion-inclusion principle, it should be the probability of being above y, and then some, you know, complicated stuff here where you have to take account of exclusion-inclusion. Anyhow, if you insist that in your assignment of real numbers to within 0, 1, to finite configurations, if you insist that that so-called drop function is non-negative, then you will always be able to, from that, be able to get a continuous valuation. And moreover, continuous valuations has been shown by Plotkin and Jones, and there's an error in that, so then shown further by Edelat and others. That can be shown to give you a probability distribution on the Borel sets, the sigma algebra generated by the able set. Okay. Okay, and here's a little example. We've got two events, A and B, which are concurrent with each other, so the event structure would just be A and B sit side by side. The configurations would look like this, and this is just the covering interval. It just means there's nothing in between here. So these are the configurations we would have. And often one sees a situation where maybe A occurs with probability a half and B occurs with probability a quarter or something like that, and then they would maybe be independent, and then the probability of them occurring together would be half times a quarter, namely an eighth. But we can imagine situations where they're not, where they may correlate in some way. And that's what's happening here. So imagine a situation where this is a configuration valuation where we have to assign 1 to being above the empty configuration. We assign half to being above A, and we assign quarter to being above B, and we assign quarter to being above A and B together. Now, in this particular case, the Borel sets are just generated by the singletons, so I can tell you what the probability, so it's sensible for me to tell you what the probability is on the singletons here. Well, what's the probability of ending up in this configuration here? Well, it's a quarter, because there's nowhere else to go. What's the probability of ending up in this configuration here? Well, it's the probability of ending up above or equal to it minus the probability of ending up here. In other words, the drop in going from here to here. In other words, a half minus a quarter. The probability of ending up here is a quarter. What's the probability of ending up in B? It's the drop in going from here to here, namely 0. There's no probability at all of ending up in B. You just you can't. In other words, if B is kind of on the way to doing A. What else do I want to say? That's probably it. That's right. So that gives you an idea how these event structures work, I hope, how event structures with probabilities work. All right. How long do I have? Okay, I just have to round up quite quickly. All right. So so given this, we can then extend. That was telling us how to put probability just on event structures. But of course, we're concerned with event structures in which some of the events are opponent events over which we have no control. So we now want to generalize that notion of configuration valuation to that situation where we have, if you like, some non-determinism in as well. So we want to make an assignment to the finite configurations, which gives us the probability of now we're thinking of configurations of being in an event structure where some of the events are labeled by minus to represent their opponent events. We want to then make an assignment to finite configurations, which corresponds to the idea that the assignment will give us the probability of exceeding that configuration conditional on the opponent events occurring. So that's what this will, the valuations will be, and they will satisfy some of the conditions you've seen before, but the drop condition will only be for drops associated with a non-negative extensions of y to later configurations. And then we want to say that we want to ensure that if you have causal independence between a player and opponent moves, then that's reflected in probabilistic independence. And although it's not clear without some argument which is given in the paper, that can be achieved in this way. We say that if you just move by opponent events from x to y, then the valuation stays constant. In other words, you're awaiting the probabilistic contribution from opponent out there in the environment. Now, I can't really say very much more than say that a probabilistic strategy now consists of a strategy as we've seen it before, where in addition we have one of these configuration valuations associated with S. And provided we restrict to race-free games, we have a deterministic copycat, so we can have a copycat in which we assign probability 1 to all of its configurations, and that will then behave like identity again. And then because of some rather technical lemma, we can actually show that in the composition of strategies, we preserve the drop condition because we can decompose the drop in a composition to drops in the component. You can't possibly understand that in the time. Anyhow, this gives us a bicategory of games with probabilistic strategies. Now I'm okay. There's a language associated with this, which works for the strategies with and without probability, and all I'll do is flash through it, and you'll see that it's based on the kind of language which supports relations, but tells us not just how things are related, how configurations are related, but tells us how they're related, and it becomes quite graphical. As you see, we have a trace operation, and we have ways of dealing with recursion, and so on. And as a special case of this, if we do the stupid thing, and we replace, and we just look at those games which are purely positive moves, we get a treatment of non-deterministic data flow if we ignore probability, and we get a treatment of probabilistic data flow if we include the probability. And moreover, if you know about this French work on probabilistic coherence spaces, it's not been completed yet, but we seem, if we specialize even further to games where the causal dependency is trivial, then we seem to get that too. All right. But I'll make a plug of something here, which is a few years ago, when I developed a lot of this, I was very proud and very pleased. But then a year ago, something started happening which made me less pleased. It was the realization that there were some, and these did not appear when I just looked at non-deterministic things. It appeared when I started looking at these probabilistic strategies. There were probabilistic strategies out there in the world that were not expressible because of the kinds of event structures I was looking at and using. And it's because the event structures I'm talking about don't properly support parallel causes. I'll just give you an idea of what the problem is, and in fact that we've solved it now, but it's taken a year. And this is described not in detail, not the solution in detail, but the problem and roughly how the solution goes is described in the paper. So we go back to that game in which we have 2 opponent moves and 1 player move. And we imagine winning this game if whenever opponent makes a move, we as player make the player move. So there's an obvious distributed strategy for doing that. We imagine this really is distributed, so we're a team of players, I send one watcher out to look at the first opponent move, and I send another watcher out to look at the second opponent move. And then, when either of them sees their opponent move, and it may well be both are made, they race back and they make the player move. With the event structures that we were using, we had to make make it such that the move by watcher 1 and the move by watcher 2 were in conflict with each other. If we do that, we find we have to split, because of the way probability works, we have to split the probability across the watcher 1 and watcher 2. There's no other thing we can do. Now, you might think, well, that's because he's doing probability in a stupid way, and I thought that myself for a while. But no, the problem is that the event structures are not supporting parallel causes. So one needs to enlarge the event structures to support parallel causes. Ah, but that's been done. It was done in my thesis, yeah, with these general event structures. But we need to, if we're talking about strategies, not just support composition like pullback, but we also need to support hiding. And general event structures do not support hiding. So the panic was on. What do we need to do it? And so with the help of a brilliant young chap from ENS, Paris, Marc de Wismer, we've solved that problem by generalizing the event structures that we've been working with to something very similar, actually. Event structures like what we've seen, but with an equivalence relation on them. And this equivalence relation says that these, if you like, it allows disjunctive events to be equivalence classes of events as we thought of them formerly. And in this way, one is able to support parallel causes and hiding, and one then can carry all of this through and get a treatment of probabilistic distributed strategies that, as far as I know, does everything we want. I've not been able to tell you about the language, which would have made this a bit more compelling, I think, but at least I've given you a rough idea there is something. The paper does describe the language in detail. Okay, thank you.
Thank you very much, Glynn, for the talk. Maybe question here?
So the way I'm used to resolving non-determinism and probability is to strategize non-determinism. So whenever to strategize non-determinism. So in the classical setting, you have what's called stochastic game, where you have two players and nature. Then you say, okay, each player, in this case, you know, opponent, what do you call your player and opponent, each has to have a strategy. Mm-hmm. So player maximizes, opponent minimizes, and nature takes expectation. So the final outcome, in some sense, is obtained by computing the expectation, the max of the mean of the expectation. Because I'm trying to optimize for me, and the opponent is trying to pessimize for me, and nature just plays expectation. And I didn't see here this basic max mean expectation in this structure. Where is it hidden?
Well, I mean, it is, you don't see very much of it here. I mean, there's first of all, you can extend these games by adding payoff functions to the configurations of the game. So in other words, you assign, you have a measurable function from the configurations of the game. So then, once you've got that, you can talk about a play off between a strategy and a counter strategy. So a strategy is like this and a counter strategy is like this, where these are probabilistic strategies. When you do that, in this particular case, you'll get a probabilistic event structure. There won't be, because you won't have any opponent events left in here, you'll have a probabilistic event structure that, because of the push-forward results of probabilities, will give you a probability distribution on A, on the Borel sets of A. So you can then take the expectation of payoff as just the Lebesgue integral here. Okay? Now, once you've got that, you're in the game, because you can start talking about you start now beginning to get the kind of min-max result that you're talking about, because you can talk about the value of a game A as being the sup over sigma of the inf over tau of the expectation of sigma tau played together. And And then you can do the same thing with a dual game, and you can say if the value of the A is the negative of the value of the other one, then you've got a value theorem, you've got a value for the game, and you can show things like if you have a Nash equilibrium with respect to these ideas, then you have a value theorem. So it got cut out, but we could start talking the same language through this. I hope that makes some kind of sense.
Only one more question. Over there.
So, is there some idea of how to extend this kind of ideas to the quantum setting? To quantum.
Yes,
setting.
yes, there is. I mean, yes. I mean, it was one of the slides. I mean, yeah, quantum games. I mean, you can if you take your game and you associate in the game A, say, you associate the moves of the game with projection operators or unitary operators in Hilbert space in such a way that concurrent events of the game are associated with commuting operators, then you get a very nice result that local to any configuration you get a probability distribution on all the sub-configurations just coming out of what I've told you, just automatically. So you can do that. So what you can do is you can talk about quantum experiments as being probabilistic experiments on quantum games. You can have them playing against each other in the way that I described to Moshe. The result will be a distributed probabilistic strategy over a distributed probabilistic quantum strategy. And then you can start doing things. Now what I don't know is how to take these latest ideas on disjunctive causes and combine it with these quantum games. It's like I want a sum of all histories idea in here, and I'm just a bit too naive to know how to do it. But there must be something waiting around the corner there. But there is, if you just look at what I've said, yeah, it generalizes and gives you quantum games that are out there, and gives you more, but it gives you the quantum games that are out there, and even gives you a kind of foundation for some of these non-locality experiments that you.
Yeah, this is what I'm interested in, because I mean, but the other question is like, would this kind of event structure approach give some way of computing the value of a quantum game, or
quantum what?
Computing the value of the game, like is there an obvious way of using these event structures to actually compute the value of the game?
Yeah. Yes, but we've not done very much on it. I mean, it got sidetracked by this kind of problem that we had of realizing we couldn't do all the intuitive strategies, and so that had to be solved first. But yes, the ideas of values of games, and I think if I've understood what you're...
Yes, I mean, I'm interested in the computation itself, because like Moshe asked, you can associate the values to the game, like duality and the payoffs, but in the quantum setting, everything gets a little bit, it's not clear that's computable even, so in this non-local...
There's not been much done on it, but you can extend the notion of game, as I said, so a game will now be associated, I should really say, the game is associated not just with these operators, but also with a density operator to stand for the initial state. And that will then give you the probability distribution. So if you take these guys, you can compose them in parallel, you can take a dual, you have, a lot of this language goes through. It's not much has been done with it. I've done some kind of, for the Prakash Panangan Festskrift, I've got some informal examples explained in a kind of rather informal way of how one might use it. But yes, I think there is potential there.
Okay, thank you.
Okay, let's thank the speaker again, please. There is one very quick announcement about dinner tonight, so Frank is going to give you a few words. Just 1 minute.
So, due to the request by many of you, the bus will first take you to at 6:15. We are a little bit behind schedule today. The bus will take you to the hotel first, and then at 7:30, it will take you from the hotel to the restaurant. Okay, so you can go to the hotel and rest a little bit. I sent you an email with all this information, also with the address if you want to go directly there. Another thing is there is a conference room change. We realized that this auditorium is too big and the other conference is too small. So we found a conference room that is more appropriate. It's right next to the cafeteria where we are having lunch these days. It's the so it's number building 15 on the campus map, next to the conference cafeteria. And there will be a brief steering committee announcement tomorrow at 12:15 p.m. Any questions about this?
When are we changing route?
It's for tomorrow on.
Not now.
Not now, no. Today is okay. So.
This moment.
no, this moment is okay. So, any other question? Okay, so anyway, I sent an email for the people who are not present. I hope they read it. Okay, thank you. So we are a little bit behind schedule, so don't be late for after the break. 10 minutes.